So welcome everyone. I would want to keep this next 45 minutes, 1 hour highly interactive, and anything that you guys have that needs a discussion, please put that in the chat. So we'll go over. So this is me having around 14 years of experience in this field now. Started out way back in 2009, 2010. At that time, there was not even a term called data science or machine learning that we typically had. Started my career with developing some algorithms around NLP, then getting some products to market in various internships. And as was correctly said, I'm an alum of IIT Kanpur and Indian School of Business. And at both these places, I approached the educational elements from a more or less mathematical and first principles based thought process. I've worked in the industry, mainly financial industry, where I've seen graphs being leveraged in various use cases. Consulted with the government, worked in fintech more recently, and realized that data science and AI ML, how important they are to today's infra of the world, essentially. I've kept this session mainly free flow. So I'll be talking to you from a perspective of somebody that's been doing this for a while. Andrew NG has recently said that, not that recently, but AI is the new electricity. Basically, the way I see it, AI would become more or less like an infrastructural element for the world going forward. What we are discussing today, graph data science, you'll discover, and I hope that you can actually capture some of the excitement about this novel and important topic from today's talk that I discovered during my work and during the various things I've done with this. So let's start. I want to actually see in the chat now. So we'll get to deep learning as well, maybe towards the end if we get some time. I'll start. How many of you have heard the name Euler? I've also written that in the excellent. So somebody even mentioned, I believe, the name of the country at that time when Euler was born. So graph analysis, network theory, everything has a origin way back 1736. And as we'll see, at the basis of ML is mathematics. And the beauty of mathematics is abstracting things, keeping only what's required and abstracting everything as well. So on this slide, I'm actually proposing to you or showing you the original problem that one of the greatest mathematicians of all times tried to solve way back in the 1700s. The Königsberg bridge problem. The king had proposed this problem to everyone as it was in those times. Nowadays, you can do applied mathematics and earn a living. Long time back, people who were doing applied mathematics, they did it purely for passion. So they had to be taken into the consideration of kings and noblemen, and they could answer back questions that were of interest to these luminaries. So Königsberg was a city which included 2 large islands connected to each other and to mainland portions of the city by 7 bridges. And the puzzle that was proposed was, can you actually walk on touching each and every island in the city without crossing any bridge twice? As is done in everything in mathematics, whether you're counting numbers on your fingers or whether you're counting the roadways through bridges, Euler first converted this into an abstract form and then took away all the complications from this that were not germane to the problem that he was looking at. The answer to this one we discover in graph theory is that it's no. You can't really walk all the 7 portions, all the 4 portions of the mainland and not traverse a bridge just once. We'll come now to this, and this is a question I want to propose to all of you here. I definitely want to see some answers in the chat box. What are the components of the graph? And let's not go into a mathematical definition here. I would assume that everybody can, information is right. Nodes is also good. Edges is there, connected point, vertices, nodes and relations, weights of edges, excellent. Features, yes. We have a lot of terms. Yes, the audience has some general understanding of, okay, this is what a typical graph is. Let me go to the next slide now. A graph is about relationships, typically. And a graph in its mathematical form or in its abstract form consists of only these 2 components. A node, which are actually numbered in this diagram, 1, 2, 3, 4, 5, 6, and edges. And typically between any 2 vertices or nodes or entities in a graph, these are kind of interchangeable words: nodes, entities, vertices. You can have 1 or even more than 1 relationships or edges. They just give rise to different kinds of graphical properties. In addition to just having a point as a node and a line as an edge, what you could also do is you could assign some properties to these nodes. So what kind of properties can a node have, guys? On comments maybe. So if this was a graph that represented the relationships or friendship structures on Facebook, what kind of properties can the nodes have? Name, age, gender, yeah, correct. And what kind of attributes or properties the edges can have? Edges, the relationships between people. A direction is one, yes. Would friends relationship have a direction? If the node 1 and 2 were friends in the general sense of the word, yes, family or friends would be 2 different relationships that can actually occur in this graph. The last line is something I've actually put up, which is basically a design principle where we'll get to in another two slides, which is a very simple one. Form follows function. The structure of the graph that we typically set up, it will guide and it will limit the questions we can ask out of the data that we are looking at. And we'll also go through a kind of a ad hoc graph data modeling exercise in this in these slides. Now let me take you to the next slide and you'll see something of 2 different graphs. On the right is a graph somebody has made on the internet, the Game of Thrones graph. And on the left, you have a social media graph where you can see various kinds of relationships, Potentially one of the relationships is that this person listens to a piece of music, or 2 people work at the same place together. That is a relationship. 2 people deeply in love is another kind of relationship. And on the right, we have the relationships taken from the Game of Thrones network. People have created an entire network of all personnel or actors in Game of Thrones, and how do they relate in terms of family ties with each other. That's the graph on the right. Just from this slide, you'll see that 2 completely different places, 2 completely different applications, and still the great data is being visualized in the form of a graph. The importance of this is that instead of having a row level view of everything, your concentration has become on the connections between the actors. Actors meaning nodes in these graphs. But these don't need to be people. The telephone cables that run from continent to continent, they can be put into a network and analyzed as a graph. The internet cables that go from continent to continent, global roadways can actually form another graph. There are some words that we discovered in the comments earlier: weighted, directed, undirected. And again, all of these are different kinds of toy graphs on the screen in front of you. So far, guys, any comments, any questions? Because after this, I believe we go into something slightly more complicated. So far, we were just getting to know what graphs are, what are the different properties or aspects a graph can have. And we discovered that their nodes, their edges, their properties of nodes and edges. So I'm building the basic infrastructure and mathematics right now, Vishubha. Yes, neural networks do use graph, and they are a particular kind of neural networks, graph neural networks. I can also provide a link for that. Fragmented is just when there are two distinct components of the overall graph that can be separated and there doesn't exist a connection between the two of them. Closure is a kind of graph where starting from one node, you can actually reach anything, any other node in the network. Okay, guys, moving on. So these are the typical things that we can actually discuss about a graph that somebody else has made. Is this a directed graph? Is this a undirected graph? What is the weight of an edge? What are the properties of an edge? How much centralized this particular graph is? Is this dense or not? Denseness with respect to graphs is the number of connections in the graph divided by number of maximum connections that that particular graph can have. Maximum number of connections a graph can have is always a combinatorial expression, NC2, and a graph that has all possible connections that can exist mathematically is called a fully connected graph. We'll go to the next slide. And at this point, I know you guys would have actually seen Excel data or worked with ML or some of these concepts in the past and potentially not used graph data structures. Then what is the point of it all is a question that you guys can now be asking, because I just rambled on for 30 minutes about the beauty of something called graph data science. Showed you different kinds of graphs that can exist. But why would somebody want to actually put things into a graph when, again, the same thing can always be represented mostly in a tabular format also. And here I'll again come to the same principle I talked about earlier, that form has to follow function. It's not like graph data science can actually be applied everywhere. Something like a house prediction exercise that all ML students kind of go through in their very first introduction to the subject. California house prediction, that typically springs to mind as an exercise where graph would not play a major role. Even if somebody converted that to a graph data model and tried to apply different kind of graph data analysis to that, it's not like that should have a major advantage. On the other hand, if the idea there became that you also had the information of loads that connect different properties or houses, and you had a lot of interconnected information about the houses. Then it would always make sense to put things in terms of a graph. So the focus has been taken away while converting the data to a graph data structure from the entities in question towards the relationships that the entities have with each other, as well as with different kinds of entities. I'll now talk about a very, very interesting thing. So guys, in 2000, so let me first explain what ICIJ is. This is a slight tangent to graph data science, but this will demonstrate to you why graph data science is useful and what it can achieve. So a lot of insiders, a lot of times actually leak out papers or emails or data leaks from all kinds of places. And ICIJ is a international organization which is cross-border, and I believe it stands for International Council of Investigative Journalism. They talk about problems that are too big for even one country to solve. So people were uploading different data sets, essentially leaked data set out of lawyers' offices in countries considered to be tax haven, Panama specifically. And they sent that to a newspaper analyst. That newspaper analyst shared that data set with ICIJ. And a lot of technically skilled people actually got involved. This is way back in 2012, 2013. What they discovered, and they started putting this document into documents and these databases and these images into traditional SQL, NoSQL databases, and trying to do typical analysis on them. While journalists were actually working in various different parts of the world, collaboration was not proving to be something that was easy. And additionally, people were discovering more and more that it was not about one organization that was actually registered in a tax haven country that was important. What was also important is who are the owners of this organization, how are they connected to different organizations that may or may not be having a registration in the tax haven country or with the tax haven lawyers that were actually in the deals. So the journalists turned to the graph data science tech stack. They discovered a graph database. They turned everything into a pure play graph, and they followed a typical analysis flow. Now, the impact of this is something that should be obvious in the image that you see on this slide. A lot of indictments and arrests were made because of the investigations that were possible on this massively unstructured and, in the traditional viewpoint, unconnected data set, from which connections were able to be gauged and insights were able to be leveraged by using the tools, techniques, and methodology of graph data science. I think at that time, shortly after this, I started working with Government of India as well. And what we are seeing here, that's just 4 newspapers, but at one point of time, this was the front page news throughout US, throughout Europe, and pretty much everywhere. A lot of very immensely important people were indicted because of this. So typical analysis flow. So these guys, this is the analysis flow taken from the notebooks of the journalists that were doing this work. So after they classified the documents, they figured out metadata, they actually determined entities, relationships, and everything. They tagged various properties to these documents or these entities, such as who was the author, what was the leak source, what was the country name, and so on. And then they inferred relationships, entity relationships, they computed similarities, and analyzed the data using graph queries and visualizations. Now, these last things we potentially would go into. So after somebody gives you a lot of data and you're able to actually transform that or parse that data throughout, at this stage, you would know what are the different entities in data, what are the different relationships between these entities. The next step, and the most important and the highly iterative step, is setting up the proper graph data model. Yes, so there is a question in chat. Could you repeat why we use graph instead of table? So Renal, I'll answer your question like this. Everything that you look at is an abstraction. Sound can be represented as a waveform on a piece of paper as well, as bits and bytes in a computer terminal, in the internals of the computer as well. And it's also an audio file. So again, form follows function. What form do you want to display or use your data in depends very much on what exactly is it that you want to do with that. So here the interest was in looking into the relationships between the different entities. Looking at data in a tabular view pushes relationships into the background. And while both can be, yes, problem statement, or rather, what is it that you want to take out of the data? The biggest mistake I believe an analyst can make is answering exactly what is being asked. The data analysis process, the data science process is always the process of discovery. So the problem statement essentially does guide to an extent, but more than that, what the analyst or what the data scientists essentially want to take away from the data. What is it that they want to understand from the data? And there are various kinds of insights that can be gauged from graphs that would not be possible otherwise. We'll get to that in just a while. So what is a graph data model? Graph data model is essentially, data modeling is often a journey into the lands of the unknown, because after you've set up a proper data model, even you cannot tell beforehand what insights you'll be able to gauge out of this. And I look at this as a journey of exploration, as a discovery, as a mapping. And just like when you climb a mountain, you want to understand what are the puddles, when the rainfall has been, what are the different valleys, and what are the different peaks. Similarly, after you set up a data model, each of these questions can become either completely obscure or completely transparent, depends upon the data model. So regarding the point that I was making with respect to why we used graph and not tabular data for doing the ICIJ analysis, it is because the graph data model illuminates what was to be illuminated there. A tabular data model would have hidden those into obscurity. And that is why getting the data model correct is not just the key, it's pretty much everything. Because after that, given enough time, either a question would be answered from the graph or the graph would just hide away its secrets in the darkness. And that depends upon what data model is actually set up. What are the nodes that you would consider a node in a graph? What are the relationships that you would consider a relationship in a graph? Whether you want to convert a node into a relationship or not, that can also happen. The two people, A and B, having a relationship of, let us say, living in the same city, called that can be converted into a different graph of three nodes, two of the people A and B, the third node representing a city, and both the nodes A and B connected to the node of city by a relationship like they live in this place, and the city name stays the same. So this is not exactly rocket science, but it can get complicated at times, and that's why this has to be approached from each possible direction. And specifically what the purpose of setting up the graph data model is. What are the questions that at the end of this graph data model? What are the questions that at the end of this graph data model setup we would actually be asking out of the graph are supposed to be listed and understood at this point of time. We'll get to centroids and centrality in a while. So till now, I've actually discussed what are the different kinds of graphs, where all this can be used. Yes, graph can predict new relationships. That would become one of the questions. So guys, here what I'm looking for on chat or on Q&A, whatever actually works out for you guys. What are the questions that after having set up a graph, something like this, or something better yet, like the left-hand side graph on this slide, what are the questions that you guys can think that you will be able to ask out of a graph? Go on. How many people are friends of A who is also not friends with B and C? That exactly you can always ask Dingu. That becomes kind of a query into the graph database that you have to write yourself, and the graph would answer back. Yes, that's a very real possibility. Like how many employees are working in the same company? Of course, this is a question that both tabular data form and graph data form would answer directly. Lalit, connections, direct, indirect, again, that doesn't become a question that has a direct physical world value. So connections themselves have to mean something. So Monica, you're thinking in terms of too much technical. I'm talking more about what are the real world questions that we can actually ask out of the graph. Because always in the data science, we're not just doing this for the beauty of mathematics. We're doing this for getting answers to be used in the real world. So we'll go to the next slide. So what can a graph answer? Typically, a graph is a representation of a complex network that exists in the real world. As such, how does movement happen across the network? What are the different influencers in the network? What are the different groups? How are they interacting? What are the patterns in the network? These are some broad categories in which questions of importance can actually be put towards a graph database. But this is not an exhaustive list at all. There are solutions nowadays, and Shantanu Sharma has already mentioned the name Neo4j. Neo4j is a very practical, very popular graph data science graph database, essentially, Shantanu. And those solutions essentially allow you to visualize data in terms of graphs and then think about new and interesting questions you can actually put up to your data set. When you do data science and ML, there are certain kinds of questions that you actually try to answer. ML model, a classification model, for example, would answer one particular kind of questions from the data set. Given a set of characteristics, what the output would be in future or on unseen data. Graphs answer slightly different questions. So if we had a graph of all the people in a subset of social media, then we can actually ask out of that network, what are the most important people within this network that everybody follows? What are the most important people within this network whose opinion essentially becomes facts for the entire network? Who are the rule makers? Who are the rule breakers? Who are the outsiders? Who are the insiders? Who are the influential participants? And so on and so forth. Social influence, something as ephemeral, as abstract as social influence, is something you can study with a graph. Movement of materials, typically you can study with a graph with a network analysis point of view. Some more pointers I put up on the slide, a lot of text. I'll probably discuss some of this in more detail. So route mapping throughout a network, essentially what Euler was doing in 1756. That is a difficult problem. And for majority of these kind of questions, nowadays you get automated algorithms that have been set up, which can pretty much answer these kind of questions. Just like you have ready-made classification, logistic regression libraries in Python, or you have a pre-trained model that essentially spits out the next word. Algorithms are already available for answering some of these questions, but whether they are the relevant questions to be asked out of a graph or not is something the analyst or data scientist gets to decide. So for a travel network graph, for a supply chain graph, for a graph for a logistics company, for a graph for an e-commerce company, the first question, how do things travel through a network? That can become really, really relevant. If you are setting up a new business in a country and you want to understand how different cities are connected, which are the cities that don't essentially lie on roadways from one city to another, that becomes a propagation question, a path finding question. Various algorithms, including the shortest path between any given nodes, are nowadays commonplace to answer this question through software and data science. What are the most influential points? And we'll touch upon this influence concept in a while. Again, see, influencers, and they can be influencers of both kinds. Positive influencers that essentially keep the network together, negative influencers that act as bottlenecks in the network. Influential with respect to either the number of connections an entity has. That's when you get into degree, out degree, in degree for a particular node. And Centrality algorithms typically answer these questions. There are various kinds of centrality: degree centrality, eigenvector centrality, relationship centrality, and so on. What are the different groups and interactions within a network? So you'll set up a network, and now you're trying to figure out what are the different participant groups in this network. So, and this particular point was actually used by the Australian police in 2016 or 17, that they were kind of going after the kingpin of a drug network, and whoever they were actually arresting, they were always turning out to be clean, and they were just not able to identify this one person. So the kingpin of the drug cartel essentially only had a minor traffic violation ticket against him. So when the police, they had Neo4j and graph data science libraries on the premise, and when they ran these algorithms, what it figured out was that even though the drug kingpin was not part of any of the communities that they had detected within their state, he was outside those communities, but he was still first degree connected or directly connected with the major influencers in all these communities. So at this point, what we're discussing is that things that the data itself is not even telling you, but that the personnel sitting on the bench using their domain knowledge. Domain knowledge here means knowledge of how crimes occur in the country, are able to predict by looking at the graph, by looking at the visualization out of the graphs. And this, so finally they caught him, and graph data science was a big key in this. What patterns are significant? And this becomes the essentially the crux of all the three things that we have seen above. If you want to evaluate the entire structure of a network, you can talk about its density, its hierarchies, its degree centeredness, the average number of connections emanating from each node. And what can also happen is that once one particular person or one particular analyst discovers a pattern that is meaningful for the problem at hand, those patterns can be coded back into the database and give rise to a different kind of algorithm, which essentially tells you whether the same pattern is actually being repeated or not. And here the significance was found from manual intervention earlier. What are the different graph algorithms? This is just some examples of this. As we talked about, connected components is a community detection algorithm. It starts from various nodes in a network and tells you how many nodes are interconnected and not connected with different entities outside that subgroup. So this green graph on the left, it has three communities, three connected components. And these are essentially communities. So these could be, if you look at the economy, these could be like criminals and office-going people, and then manual labor, something like that. Minimum spanning tree is another algorithm that kind of rearranges a graph in such a way that using the minimum weights on the edges of the undirected graph, how you can traverse from point A to point B. Page rank. Page rank is also centrality. And this is, by the way, a long time ago, how Google's page rank was implemented. This is a special kind of centrality. This is called eigenvector centrality. So eigenvector is the same eigenvector you guys would have heard of in your PCA or your different matrix decompositions as part of usual ML courses. I'll finally want to touch upon centrality a little bit more. So degree centrality is just the number of nodes that you're actually connected to. And here I would want you guys, if everything as in this lecture or this discussion you actually forget, take away these key points. So centrality or importance in a social network, in a network made of entities, whether those entities are corporations or individuals, importance or significance can have various meanings. The number of people you know, the number of people that you can actually call on the phone, that probably means your degree centrality, how many people you're directly connected with. Eigenvector we'll talk at the end. Betweenness is that if you were to actually go from one person to another in a social network, on all of these parts, out of all such parts that can exist in a network, on how many one particular node will lie. So in a social network, or even in a criminal network, or even in a financial network, these kind of people having a high degree centrality can become intermediaries in enabling different transactions. Or they can actually act as brokers for different networks to get together. Closeness centrality. If you look at path from one node to all other nodes, what is the node that is actually on an average closest to everything else as compared to other nodes in the network? And finally, we look at eigenvector centrality. So in this, you're not looking at the centrality of a node itself. You're looking at the centrality of the nodes that are 1 degree separated from that. So if you remember, in page rank, important sites sending a link to one website counts more. This was one of the principle from the earliest page rank that was developed. And here again, important sites, if that is defined in terms of centrality, then eigenvector centrality, the node having the highest eigenvector centrality in a network is the node that is connected to the movers and shakers in the network, is connected to the most important web pages, is connected to people of power. And guys, this is...
we are actually running out of time. It's 7:55. So I would suggest...
Correct. So we're also out of slides. So guys, this was about graph data science. And
actually,
please go on.
You can like go through question and answer section so as to answer the questions.
Yeah. Makes sense. So yes, difference between a graph and a chart. Charts are completely different. And I do see a question here. Can we use centroid in graph to explain clusters of graphs? I believe that refers to centrality. And yes, centrality is typically very similar to what centroid of a triangle is. Centroid being the place where the medians to each opposite side essentially meets, being the most central point of a triangle. Similarly, this is centrality measures that we have. So there is Vellore V. Sasikumar. in graph data model, the presence of, so domain expert is almost always needed in understanding what questions kind of should be asked out of the graph that would essentially dictate how the graph data model should be set up. And lastly, when you go towards culling out patterns for the graph, then the domain expertise is needed. We've discussed about Neo4j. There are a lot of practical issues in graph data science. Always not setting up the correct graph data model comes to bite you. And as part of my experience, we set up the biggest network analysis graph database in the world. And even at our level, we had to remake the graph data model a couple of times because not every possible question that you can ask out of a graph essentially appears in front. Extraction of relationships, that becomes a very, very straightforward good query in any graph solution. So, and Neo4j is not the only one. I'm not advertising any particular solution here. I believe network X is another one available with Python, and there are more graph databases and graph data analysis software available out there. Influencing of networks, fairly similar to Centrality. Graphical structure we have discussed. So we have discussed majority of these questions now. Let me drop off, guys. It was wonderful interacting with all of you. Let's talk again soon.